So what can we use these bit operators for? Well, one useful application is to enumerate subsets. So let's look at this lead code problem called subsets. So we are given a set of different integers, and we want to return all possible subsets. So in other words, we want to return the power set of this original set. So given a given so first question is, given a set of n numbers, how many subsets are there? I think many of you know the answer. It's 2 to the n, and the reason is for every element there are two choices, whether we include that element or we don't include that element. So because there are n elements, so there are 2 to the n choices. So 2 times 2, there are n 2 times together. So if that's the case, then for this question, how large of n can we handle? So because we actually need to return all the subsets, so when it's not just enumerate through all the subsets, we actually need to construct them and return them. So I would say n probably around 22, 23. So assuming that we are only allowed to run within a second or 2 seconds, because it's 2 to the n and then times some at least times n. So yeah. So n is if n is 20, it should be pretty comfortable. But when it's getting over 20, then we need to get careful. I'm pretty sure if n is over 25, this enumerating this will not be efficient enough. And I forgot whether I explained the reason or not. But essentially, the hardware can carry out operations at a particular rate, and I think most of you know computer. We characterize the speed by gigahertz, like CPU have 2 gigahertz or 2 point something. So gig essentially is 10 to the 9. So the 2 gigahertz, that means every second it can perform 2 times 10 to the 9 operations. So the computation we are doing here, they translate into actually a cycle. So some of the operations that takes just 1 or 2 cycles, some of them take longer. So it's a rough estimate. But essentially, if we count the operation in our program, if it's less than 10 to the 8, then it's probably okay. When it's the program will run probably within a second or two. When it's over 10 to the 9, then in general it's not going to be fast enough. So 2 to the 20 is 1 million, so that's 10 to the 6. So even if for every subset we do some operation, that's still pretty comfortable. So n is 20 would be fine, but if we get to 25, it'll be probably not efficient enough. So here's a C++ code for generating subsets. So given a set which is specified using a vector, so we get its size, and then we will return this is the set of set that we are constructing. So because we said we can interpret each subset as specifying for every element whether it's included or not. So we can use bitmap to represent subsets. So essentially, when we go from 0 to 2 to the n minus 1, these 2 to the n numbers will represent all the bit patterns. So we can interpret every bit as indicating whether to include one particular element or not. Then each of the integer will represent a particular set. So there's a one-to-one mapping between all the integers from 0 to 2 to the n minus 1 and all the subset of this n element sets. So this is what we do. So then I will loop over through this. So each I represent a subset. Then within here, we'll loop over j from 0 to n minus 1, loop through all the elements. So we check whether the j's element bit is set, the j's bit is set. If it is, then we will include this element. If not, we don't. And we check that by doing this. By one left shift j, this will give us 2 to the j. And then we do bit end with I. So then this will just checking whether that bit, if that bit is 1, then this is non-zero. If that bit is 0, then this becomes 0. So this has a single bit at 1, everything else being 0, mask all the other bits. So this is the way we check whether that bit is set. And after this loop is done, we constructed this subset, and then we just add it to the answer. And the same logic is implemented here in Java, so I will not go through this, but for those of you who either know Java or are going to learn Java, you can take a look and see the differences.